Hi, I'm Tim.
And I'm Chad.
And today we're going to share with you a project that we did on the movie Pirates of the Caribbean. There's just many scenes throughout this movie that have tons of physical problems that we could try to solve.
When all was said and done, we ended up picking two scenes, one of which had to do with Archimedes' principle. Let's take a look at that scene.
This is either madness or brilliance.
It's remarkable how often those two traits coincide.
Alright, now let's take a look at the free body diagram to see if Jack's feat is even plausible. So first things first, we have to draw a free body diagram. We'll put Will in the back of the boat and Jack at the front of the boat. Will weighs in at 70.9 kilograms and Jack at 60 kilograms. The approximate mass of the boat is 45.45 kilograms. And its approximate volume is 1.13 cubic meters. So the second thing we need to do is sum the forces in the downward and upward directions. The downward directions will be our gravitational forces. If we sum all the masses of all the objects together and multiply that by the acceleration of gravity, we get approximately 1810 newtons. If we sum the buoyant forces in the upward direction, multiplying the volume of the boat times the weight of the water that it would displace, we get approximately 11,400 newtons. If we take both forces and sum them together, calling up positive, we subtract the gravitational from the buoyant and get about 9,590 newtons upward. A standard gold coin, like the ones portrayed in Pirates of the Caribbean, weighs approximately 0.0067 kilograms, whereas a coveted gold bar weighs 27.5 kilograms. Both of these objects could potentially be used as weights to increase the gravitational force downward. Alright, now let's take a look to see just how many gold bars or gold coins Jack and Will would need to stay on the bottom of the ocean. On Earth, the amount of newtons necessary to hold Jack and Will at the bottom of the ocean can be equated in kilograms by dividing it by the 9.8 meters per second acceleration of gravity. If 1 bar of gold then weighs 27.5 kilograms, we would need approximately 36 bars of gold. The same process can be used to approximate how many gold coins are necessary by equating the newtons to the 978 kilograms and dividing that by 0.0067 kilograms per gold coin. This then is approximated to 145,000 gold coins. This incredible quantity of gold coins is likely much more than what is portrayed in the chest in Pirates of the Caribbean. So, our friend Jack would likely end up looking something like this. As we see from the calculations, unless you're an undead pirate zombie, you are going to be physically unable to carry that boat to the bottom of the ocean per Archimedes' principle.
That's right. Now let's take a look at the next scene that we picked from the movie. This one involves Newton's second law, and we're going to draw some free body diagrams to kind of show what happens. Let's take a look at the clip. Okay, now let's actually take a look at the physics and apply Newton's second law to see if Will's feet would actually shoot that high.
So, much like the other problem that we did, the first thing we need to do is draw a free body diagram of the different things that will be involved. So this time we'll have Jack on the left, and we'll have Will Turner standing on the cart on the right side. Jack, curled in a ball, takes up about a meter of space with another 3 meters to the ground, making another 4 meters in total from the top of the beam to the ground. We're going to be summing up a couple of different forces here, but we're going to start with Jack Sparrow weighing 68 kilograms as he falls to the ground. His potential energy as he falls will be equal to his mass times the acceleration of gravity times the height that he's falling, which all told gives us about 2,000 joules of potential energy as he falls. Next thing we're going to do is sum the force of Will as he's standing on the opposite end of the cart. His mass of 70.9 kilograms will be multiplied by the 9.8 meters per second of gravity, giving 694.82 newtons of force downward. Now, taking these two forces, we can determine the actual height that Will would fly, which is roughly 2.88 meters, 1.22 meters short. Let's take another look at that clip. So we see at this point, this is probably more likely the 2.88 meters that Will would fly, as opposed to this, which is more like 4 meters or completely out of the scene.
Okay, so now that we've seen that it's physically impossible for Will Turner to actually launch that height, let's see just how much Jack would have to weigh by adding gold coins or gold bars to actually get him to that desired height.
So the first thing that we're going to do is we're going to use the desired height of 4 meters to determine just how many newtons of force Jack would have to fall with in order to launch Will that desired height. It ends up being 2,779.28 newtons. And we'll divide that number by the gravity and the height that Jack falls to get the weight in which Jack would need to weigh, which is 94.5 kilograms. We're going to end up taking that number and subtracting Jack's actual weight, which is 68 kilograms, to get the difference of weight that we would need, which is 26.5 kilograms. We'll divide that by 0.0067, which is the weight of 1 gold coin, to get 3,955 coins. Or we can divide that number by 27.5 kilograms, which is the weight of 1 gold bar, which gives us 0.96 or about 1 gold bar.
Thank you all for watching our presentation. We hope you learned something about Archimedes' principle, Newton's second law, and the magic of Hollywood.
We certainly learned a lot in making this movie, and we really enjoyed it, so we hope that you enjoyed it as much as we did making it. So again, I'm Tim Heidecker.
I'm Chad Warheim.
Great job!